So, welcome to the week 3 live session for Analog Electronic Circuits NPTEL EE74 course. And today we will solve some questions that will help you have a deeper understanding of the week 3 assignment and help you solve the assignment. So, these questions will be similar to week 3 assignment, but some values will be different. So, please do not uh, copy these similar answers into your assignment, and please be careful while solving your answers. Okay, so first question is uh, this. Okay. Okay, so in this question, what we have to find the DC operating points, and the similar DC operating point will be used throughout the assignment. And we have been given VT is 0.5 volts. ID equation is given, and it is saturation, right? R1 and R2 are 4 mega ohm and 1 mega ohm. We have to find RS such that ID is 119 microamperes. Okay, so let's try to solve this. So this is the circuit I have just drawn that. So here K value is given, VT is given, and ID is given. So we will use this formula to find VGS minus VT first. Let's see. Let's find all the unknowns. So with this we will get VGS minus VT equals to under root ID by K, right? So VGS minus VT, so it will be under root 119 microamperes by 4.12 millisiemens per volt. It will be 0.17 volts if you solve this. Then we know VGS minus VT equals to 0.17 volts. VGS means VG minus VS minus VT equals to 0.17 volts. VG, okay, we have to calculate VG first. So for that, this is just voltage. This circuit is the voltage divider, right? So VG will be R2 by R1 plus R2 into 5 volts. It will be 1 mega ohms by 4M plus 1M into 5 equals to 1 volts. VG is 1 volts, right? So 1 minus Vs minus VT is 0.5 equals to 0.17 volts. So if we just put Vs there, Vs equal to 1 minus 0.5 minus 0.17. Vs will be 0.33 volts. So we know so what is Vs? Sorry, I forgot to tell. This is Vs, voltage here. So Vs is actually the voltage drop across Rs. So we know Vs, we know ID, we know the current through this branch. Then we can find Rs, right? So Rs will be ID 0.33 volts by 119 microampere. This will give us Rs equals to 1773 kilo ohms. Okay, so any doubts in this question? Please feel free to open your mic and tell, or you can write in the chat. How VS is zero point 0.5? Bhuvnesh, VS is not zero point 0.5. VS we calculated to be 0.33. Bhuvnesh, can you please open your mic and tell what is your doubt? I'm unable to understand what you're asking.
I got it, sir. I didn't see properly, sir. I got it.
Okay, okay, okay. So let us move to the next question if there are no doubts. Okay, so in this question, so for the same for this same circuit, we have to now find GM. So I hope you remember what is GM. GM is transconductance. It is so whatever any trans quantity is always ratio of output by input, and since it is conductance, it will be output voltage by input current, right? Oh, sorry, output current by input voltage. Then we will get conductance, right? So we have seen earlier in videos and in the previous session also, Gm equals to del ID by del VGS. VGS. So this is the output current and this is the input voltage. And we know ID is K VGS minus VT whole square. So del ID by del VGS equals to 2K VGS minus VT. So this is GM. So let's put the values now. 2 into K was 4.12 and VT, or we can directly put this VGS minus VT value to be 0.17. So let us put this 4.12 millisiemens per volt into VGS minus VT was 0.17 volts. So if we solve this, we will get 1.4 millisiemens GM equals to, or if we put it in micro, it will be 1400 microsiemens. So this one is the answer. Any doubts in this part? Okay. So let us see the next question. So let us read this one first. For the device in the earlier circuit, okay, the current is not exactly to the earlier okay equation, but as follows. This lambda is 0.14. What is R naught of the device? Okay. So I hope uh, I talked about this equation in the last session also. So this is due to uh, let me tell you, lambda is channel length modulation parameter, right? So earlier ID was K VGS minus VT whole square. So there was no dep uh, there was no dependence on VT, on sorry, on VDS, right? It was independent of VDS. So if we draw ID VDS curve, ID VDS, you would get something like this. So in saturation, with increase in VDS, when VDS was increasing, ID would be remain constant due to this equation. But now there is a factor 1 plus lambda VDS, that is the due to channel length. Yeah, so now there is a factor 1 plus lambda VDS due to channel length modulation. So now our curve would be something like this, right? If it is varying with, let me draw like this. So now our current is varying with VDS. It is not constant anymore. So it is due to this factor lambda, and R naught is, we talked about R naught also. So R naught will be uh, uh, the slope of this curve, right? So here, if we see the slope here, slope is 0. So R naught will be 1 by slope. So that would have been infinity. But now the slope has some finite value. So 1 by slope will be something finite, and that will be R naught. And R naught is actually output conductance, sorry, impedance. That's it, impedance, output resistance. And it is, R naught is 1 by GD. Where GD was GD or G naught, whatever you call it, G naught or GD. It is output conductance. So we can say 1 by R naught equals to GD equals to del ID by del VDS. It is change in output current due to change in output voltage. That is why it is output conductance. Okay. So anyways, so let's try to solve this. Now let us use this equation to find some relation between R naught and lambda, so that we can find it. So ID, let me just erase this for now. So ID is just to, let me put it in a new page. ID equals to K VGS minus VT whole square 1 plus lambda VDS. So del ID by del VDS. This is GO or GD equals to. So it will be equal to K VGS minus VT whole square dot lambda, right? So we just have to differentiate this part, right? Only here it is VDS. So only lambda will remain here, and this term would act as a constant that will be multiplied. So we will get K VGS minus VT whole square dot lambda, and it is actually ID dot lambda. It is GD. So RO will be 1 by GD equals to 1 by ID dot lambda. So we knew ID was 119 microamps given in the first question, and lambda is 0.14, sorry, 0.014. Lambda is 0.014 per volt. ID equals to 119 microampere. 0.14. So R naught we will get as, if we solve this, we will get 600.24 kilo ohms. So this is the answer. Yeah, here it is. Is there any doubt in this part?
Sir, what is the value of ID?
ID is 119 microamperes. It is the same value as given in question 1. We will take the same value throughout all the 10 questions. It was given, yeah,
Okay, sir.
here 119 microamperes.
Okay,
So
sir.
I think in your assignment also there is written that we have to use the similar values in all the questions. So these values of R1, R2, RD, whatever we calculate, they will work for all the questions ahead also. Any other doubt?
No, sir.
Okay. So let us look at this question now. So it is a very interesting question. So what do we need to do is we need to find the value of RD such that device is in saturation and the drain voltage can swing up and down around the operating point, and throughout this swing the device is on and in saturation. Okay, so I'll tell you what this thing means. What else is written? Assume that the voltage at the drain will change sinusoidally. Okay, and voltage at the source and gate are constant and not changing. And what is the RD suggests? So this is an important line. What is the RD such that the amplitude of the sinusoidal swing is maximum? So we have to find this such that the swing is maximum. Okay, so what does this mean? So let me tell you. Let me draw here. So let's say this is VDD 5 volts, this is RD, and this is the MOSFET, right? This is some other circuit. I'm not drawing that. So here we have VD and this is RD, right? So what they are saying is at VD, it is swinging. The voltage is there's an AC component that is swinging like this sinusoidally, right? They have written. So what should be the DC voltage here such that these swings do not always keep them in saturation, right? So uh, let us suppose the voltage here was let's say 1 volts. So if it swings, let's say uh, zero point 0.5 volts here and zero point 0.5 here, so it must remain at saturation. So here it will be, if this is 1 volt, it will be 1.5, it will be zero point 0.5, right? So it should be in saturation at 1.5 also and zero point 0.5 also if I keep VD at 1 volt. So we have to find such value of RD that will maximize this swing. So we need to keep on increasing this swing and at the same time maintain it in saturation. So let us see how we will do that. Okay. So first we will find the upper and lower limits of VD such that MOS is in saturation. So what we will do first is we will first find these these top and bottom values, and within this we have to swing VD, right? So we need to find these edge cases where it will be in saturation. Then we can place VD somewhere in between to maximize this, right? So let me draw again. So for saturation, VDS should be greater than equal to VGS minus VT, right? So VDS is VD minus VS should be greater than equal to VGS minus VT. We had solved this VGS minus VT earlier. It was 0.17, 0.17, and VS we had found to be 0.33. So if we use VD minus, so if we put this, VD should be greater than equal to 0.5 volts. Okay, let me call it VD minimum. So the minimum, uh, so this VD should be minimum equal to 0.5 volts to keep this transistor in saturation. Okay, so to find the maximum condition, so VD can always be greater than equal to this, right? So maximum can be anything. And what maximum do we have? The max we have is 5 volts. So let me draw this. This is 5. It's 5 volts. This is VD. If ID current is flowing, so VD equal to 5 minus ID RD, right? So at the edge, when VD is equals to 5, equal to 5 minus ID RD, then ID will be 0, right? If this is 5, if this is 5 and this also is 5, that means no current is flowing through here, right? That means ID will be 0. So this is the other edge case, that maximum VD max is 5. VD max to 5 volts. So we have VD min and VD max. So what do we have right now is we have this value, this is 5 volts, and we have this value, this is 0.5 volts. Now for these to maximize these without moving into out of saturation, we need to place VD exactly in the middle of this, right? So VD we will place as 5 minus 0.5 by 2, that is 4.5 by 2, 2.75 volts. Now for we have selected one VD, but our aim was to find RD. So for this VD we will find RD. So we will use this same equation, VD equals to 5 minus ID RD. So 2.75 equals to 5 minus ID. ID we know 119 micro RD. So RD equal to,
Excuse me,
yes,
I think there is a calculation error. VD should be equals to 2.4, 2.25.
okay, yeah, fine, 2.25, let's say. Okay, wait, this will be, yeah, this is, I've done it wrong. It will be 5 plus 0.5, 2.75 only. Why I'm saying this is, we know this difference is 4.5, right? But this is the difference. But in respect to ground, I will have to apply here 0.5 plus 2.25, right? To maintain it at this middle level. So it will be 2. So that is why I have to do 5 plus 0.25 by 2, or you can also write it like this, 5 minus, let's say, 2.25 plus 0.5 we will add later, so that we get 2.75. Uh, can you confirm if this concept is clear, or I'll repeat this part?
Please repeat, sir.
Sir, repeats.
Okay. So our aim is to place VD in the middle here, right? So that we can have maximum swing. So uh, our minimum point is 0.5 volts. Our maximum point is 5 volts. The difference is 4.5 volts, and this you are correct. This difference will be 2.25, and this will be 2.25 volts. But what we are doing is we are setting some voltage here. That voltage, if I okay, if I set this voltage to be 2.25 volts, so uh, 2.25 minus 0.5, what this value would be? Can anyone tell me? 2.25 minus 0.2,
1.75.
1.75, and here it will be 5 minus 2.25. It will be 2.75, right? So this is not balanced again. So why did this happen? Is uh, because we directly put this 2.25. We have to put this 2.25 voltage with respect to ground. That is, we have to put uh, this 0.5 plus 2.25 here. So if we put 2.75 here, we'll get these equal. Am I still not making sense?
Can you repeat it, sir?
Okay, let me open a clear page. What do we have is, we know this is 5, this is 0.5. What is the middle value for a sine wave? So what we know is this amplitude, and this amplitude we can tell, right? So let's say this amplitude will be 2.25 here and 2.25 downwards, right? So this is, let's say this is 0. Let's say omega t volts. So if this is 0, this is 0.5, this is 2.25. Okay, it is not actually 2.25. This is what we have to find. This is VD, let's say. This is 5. So what would be the amplitude of this sine wave? It will be only 2.25 sine omega t only, right? But for to what is the that is this complete signal, it will be, okay, it is more confusing this way. Let me just tell again like this only. This is 5 volts, this is 0.5 volts. this difference is 4.5. Half of it is 2.25. So, uh, so if this voltage is 0.5 volts already here, right? It is 0.5 volts. This value will be 0.5 plus 2.25 volts, right? This value will become 0.5 plus 2.25 volts, that is 2.75. Now if we add 2.75 more, we will get 5 volts. If we add plus 2.75, we will get 5 volts. So that is why we are taking it to be 2.75, not 2.25. Does this make sense?
Yes, sir.
Anybody wants me to repeat this?
Sir,
Yes.
sir, can I say it as the average of two peaks?
Yes, essentially, mathematically, it is the average of the two peaks. Yeah. So, anyways, if it is clear, it is 2.75. Let us move on. So, we were here, VD equals to 5 minus IDRD, and VD we have chosen 2.75 equals to 5 minus 119 microamps into RD. So, RD will be 5 minus 2.75 divided by ID. It will be 18.907 kilo ohms. So this is the answer, 18.907 K, and yeah, it is given here. Is there any other doubt in this question? And or if you want me to repeat any part in this question?
Sir, the video will be shared later, no, sir?
Yes, I will upload on the YouTube channel.
Okay, sir.
Okay. So if there is no other question, I'll move ahead to the next part.
Yes, sir.
Okay, so this is now we have AC coupling in the circuit. We are applying, so this 5 volts and these resistors were actually biasing uh, our circuit at some DC values. We had some ID and VDS and VGS. These are DC values. Now we are applying an AC signal here. V in. This is an AC signal. So onto that DC, we are applying AC signals. And with AC comes gain. So we have to find voltage gain for this circuit. So if you see clearly, we are applying input at gate and we are taking output from drain. So this is common source amplifier. And if you have seen videos, the gain of common source amplifier is minus GM Z out, right? So this is simply the gain of common source amplifier. Anyways, we'll try to solve it a little further so it is more clear. So what do we have? RL is 20 kilo ohms and this RA is also, these both are 20 kilo ohms. Okay, nothing else is given. R1, R2, RD, all these values we'll take that we had previously only. Okay, so this is the same circuit. I've just written all the values and drawn it. RS we found out in previous question. RD we also just found out. So our first step is to find this the small signal voltage Vg here. So if this is V in, what is the voltage reaching here actually at the gate of the MOSFET? So this is simple voltage division. So Vg equals to R1 parallel with R2, R1 parallel with R2 plus RA V in. So this will be 4 mega parallel with 1 mega divided by 4 4n parallel with 1n plus 20k. So this will be something Vg equals to 0.9756 V in. Okay. So next thing is to find Z out. So okay. So if we have anything at the drain here, so the impedance seen here is R out or 1 by GD. So here what will be the output impedance? It will be seen, the impedance seen here will be, let me draw this. Z out will be R out, we know just from the transistor. From the transistor it will be R out. It will be in parallel with RD because we have RD connected and also RL. So this is the complete output impedance at the drain. This is the output impedance at the drain node. Okay. So anyways, so our gain VO by VG is equals to minus GM Z out equals to minus GM RD parallel with RL parallel with RO equals to GM value we have calculated previously. Let me see. Yeah, one 1.4 millisiemens GM. So minus 1.4 millisiemens RD is 18.907 K parallel with RL 20 K parallel with RO. RO we calculate earlier, it was 600.24 kilo ohms. RO we have calculated, let me see where. Here we have calculated RO. Yeah, 600.24. Anyways, so if we solve this, we will get minus 13.3883 VO by VG. But our actual gain is AV, equal to V out by V in. So we can write it as VO by VG into VG by V in. So it will be minus 13.388 into Vg by Vn is this. This is Vg by Vn, 0.9756. We will get minus 13.06. This is AV. And this is the answer, and yeah, this will be the answer. Any doubts in this part?
No, sir.
So I hope you have seen this minus GMZ out. So it should have been in, I think, week 2 videos, if I'm not wrong. The gain of a common source amplifier. Yeah, anyways. Question 6. So in question 6, we have to find the power gain. So power at load, that is output, power at output, and power available from source, that is input. So power available at input, let's say P in equals to, it is given to be this value, VI square by 4 RA. So where does this 4 comes from is something you might have studied in yeah, any networks course.
Maximum power transfer
Yeah,
theorem.
maximum power, due to maximum power transfer theorem, we match the input and output impedances. That is why we get this 4, right? Okay. So just I wanted to point that out why there is 4. Next is what P out is. P out will be V out by RL. Okay. So we have to find gain, that is P out by P in. So if we put it like this, oh, sorry, V out square by RL. V out by RL is current, not power. Okay. So how we can write this P out, V out as AV times V in, right? VO by V in equals to AV. So VO, AV, V in. So if we put this AV square, V in square by RL. So we put it here, AV square, V in square by RL divided by V in square by 4RA. V in square cancel. We will get AV square 4RA by RL. What was AV? AV was 13.606 square. RA was 20 kilo ohm and 4, sorry, and RL was also 20 kilo ohm. So cancel this, we will get 682.25 gain. Now we have to find it in decibels. So gain dB equals to 10 log 682.25. It will be 28.34 dB. So this will be the answer. Any doubts in this part?
No, sir.
Okay. So now this question. So what do we have to find? Or is the input current source resistance? So input is now given it here at source and output is taken at drain. So what kind of amplifier this is? Input is at source and out, sorry, and output is at drain. It is
Common gate.
common gate, right? Okay. So we have to find the trans resistance. Let's call it RT. That is V out by I in, and okay, R naught is assumed to be infinity. Okay, so let us solve this. Okay, so for this question also, okay, let me see. Okay. So for a MOSFET, the impedance seen from here is R naught or 1 by GD, but when seen from here, it is 1 by GM. Uh, Actually, it is 1 by GM plus GD, but we ignore this because GM is very large, so we assume it to be 1 by GM. So what we have here in this part is, let's say we have 1 by GM. This is the intrinsic part of the transistor. Then we have a resistance RS, and in parallel we have RL, right? And here it is current source I in. So IN will, okay, let me replace this like this, RS parallel RL, right? Because it was parallel anyways. So IN will go in this branch and this branch, but we want to find current in through the MOSFET. So we can apply the concepts of MOSFET, right? So let me call this current as ID. So we want to find ID here. So ID will be, so it is just division of current. ID will be RS parallel RL divided by 1 by GM plus RS parallel RL into I in.
Sir,
Okay.
is it RA or RL?
Sorry. Oh, sorry. Yeah. Let me check what is it. It is RA. Yeah. Right, RA. RL is at the output. Yeah. This is RA that is at the input. Thanks for correcting that. Yeah. Okay.
Okay, sir.
So now the current at the, so we have found this current. Now it will again divide here and here. We are interested in this component since we want to find the output voltage here. So let us call this IL. So again by voltage division, IL will be RD by RL plus RD into ID, right? And V out will be RL into IL. So it will be RD RL by RL plus RD into ID. This is V out. Let me put it here again. RD RL divided by RD plus RL into ID. So we will put the value of ID here. It will be RD RL RD plus RL. And ID is, let me copy it, into RS parallel RL divided by 1 by GM plus RS parallel RL. Okay. Into I in, V out. Now V out. So if we put this I in here, we'll get V out by I in RD RL divided by RD plus RL RS parallel RL 1 by GM plus RS parallel RL. So if we just put this, we will get our answer, and if you solve it, you get equal to 4920 ohms. That is our RT. This is the answer. We know every value. RD we know it is 18.9907K. RL equals to 20K. RS is 2.773K. Uh, GM we know 1.4 millisiemens. So if we put all these values, we'll get this. And it matches with this 4920. It is very close. So this is the answer. Any doubts in this question?
No, sir.
Okay. So again, the next part is very similar, where it says you have to find the power gain. So again, P in will be I in square RA divided by 4. Again, 4 factors due to maximum power transfer theorem. And P out will be V out square by RL. Again, we can write V out uh, by V by I in as RT, and RT is what we just calculated here. This is RT, V out by I in. So equals to RT square I in square by RL. Now gain equals to P out by P in equals to RT square I in square by RL. I in square RA by 4. I in square cancel. RT square into 4 by RL RA. So RT we know is 4920 square into 4 by RL is 20K, and RA is also how much is RA is 1 kilo ohm, 1K. So this will give me 4.86. Now again in dB, 10 log 4.86, it will be 6.866 dB. This is the answer. Any doubts in this part? Okay. So if you see the pattern of all these questions is very similar. First we calculate the gain, then we calculate the power gain. So now it is the last circuit, that is what we have here is gate source drain. We are taking input here and output here. This is common drain. So sir has discussed this heavily in the uh, first lecture of this week. So I'll do this one very quickly since we have very less time. Okay, so again, we need to first find the voltage here, VG. VG equals to R1 parallel R2 divided by R1 parallel R2 plus RA dot V in. VG again will be 0.9765 V in. Since all these resistance values are same, so it is also same. So let us call it K. VG equals to, let's say, KV in. Okay, so voltage gain will be VO by V in. So I'll directly write the formula. Sir has solved it in the video. So if you see the formula, it is GM by GM plus GDS plus GL plus GS. What is this? GM by GM plus, I'll write GDS is 1 by R naught, GL is 1 by RL, and GS is 1 by RS. Okay, so one more thing is we need to multiply K here. Since this is VO by V, so this is actually VO by VG right now. So if we multiply K, it will become VO by V in. So K, K. So if we put these values, we know GM equal to 1.4 millisiemens, RO is 600.24 K, RL is 20 K. Is it 20 K? RL is 1K. 1K, and RS is 2.773K. So if we put this value, we will get AVS 0.494. Okay, so this part is done. 0.494. This is the answer. So I have not solved it completely. I have just directly put the values in the formula that is told by sir in the first video. So if you have not seen it, please go see the first video of this week.
So what is K, sir? GM
Sorry,
into K. GM into K. K value what, sir?
this K is this.
In the
This
gain.
is K.
No, sir. During gain calculation, sir, GM into K you have written. V out is equal to GM into K by GM by GDS by plus GL plus GS.
Yeah,
K value what is the K value, sir?
this K value is this 0.9765.
Okay, sir.
Okay, so okay, let me tell you again. If I remove this K, so this will be GM by VG. If I remove this K, right? But now what do we want? We want VO by V in. It is VO by VG into VG by V in. VG by V in we know is this K, right? So that is VO by VG into K. So here I've taken a shortcut. I've removed this VG by V in and multiplied K directly to get AV. So if I do that, V in and K. Is it more clear now?
Yes, sir. Yes.
Okay. So the last question is again power gain. Okay. So P in is again, like we have seen earlier, V in square by 4 RA, and P out equals to V out square by RL, and V out is nothing but AV V in, PV square V in square by RL. So gain will be PO by P in AV square 4 RA by RL, and if we put these values, AV we have solved to be 0.494. RA is, how much is RA? 20K. RL equals to 1K. So if we solve this, we will get 19.55, and gain in dB will be 10 log 19.55. It will be 12.91 dB. So this one will be the answer. So it is very similar to the previous one. So so this was the last question. So you have if you have any doubts in any of these questions, please let me know. Else we will close this session for today.
No doubt, sir.
Can go to calculations in fourth question.
Okay. This.
Exactly. Yes, sir.
So do you have any doubt in this anywhere?
Okay. Okay, sir. Getting sir.
Okay. Anybody else has any question?
Sir, can we go to question number 8?
Okay. This.
Yes, sir.
Yeah.
Uh, Here, can we take this P in equal to in terms of voltage also?
Uh, since we have this relation with V out and V in, or so V out I in, we prefer it to be this way, right? So that we can cancel this input term from both input and output. So
Okay.
if we take it any other way, we will have to take, if we take it, let's say, uh, V in, our output should also have, we should have some relation between V out and V in then.
Okay. Okay, fine. Thank you, sir.
Okay. Okay, so we will stop here and I will share the video on my YouTube channel, and I think the link of that is shared in the NPTEL course website, and I will share these slides also. Thank you, everyone.
Thank you, sir.
Thank you.
Thank you, sir.
Thanks.